Okay, so the first topic today is how Linux commonly fixed Bufferbloat by Stephen Hemminger. Please start. Well, nice to see you here in St. Petersburg. We know you from the internet for other conferences and presentations, and now is your time to explain us this topic. Thank you.
Thank you. Well, I'm very glad to be here, but you really didn't have to bring the snow for me. I'm one of the community of people that solve Bufferbloat. I want to make that completely obvious from the beginning. This talk is about Bufferbloat, and it's not super technical. Maybe you'll learn something. And the word Bufferbloat, let's get this thing working. On works. Go. Oh. I will do it the old-fashioned way. So Bufferbloat started back in about 2005, I think. Jim Gettys sent an email to me and several other people, said, "Why is my internet slow?" Many other people had the internet be slow to them, but many of those people never actually did any investigation as to why. And Jim Gettys, who had been involved in the HTTP standards and X Windows, went a little deeper and dug below the surface and figured out that what was going on was traffic one way was interfering with traffic another way. You can go ahead. So with Bufferbloat, the fundamental thing of the problem is the network seems slow because it's getting choked with capacity. Now, you may be familiar with this. I don't know. I'm sure it happens in Russia. It happens all around the world. You get at rush hour. You have a nice big highway. No matter how big the highway is, it fills with cars. That's pretty much is what's going on in the internet. And part of the problem is the way the internet has evolved, everybody has benchmarks. So, oops, what did you do? I think the cable got bumped. So people typically run benchmarks down here that measure things like how much throughput you're getting on the internet. They measure iPerf, whatever. Or they measure latency. They say, well, what's the ping time? Or maybe they measure the fairness of two streams. But in my house and everybody else's shared internet, what matters is the middle, where all of these things have to work together. And Bufferbloat happens when the bandwidth starts to build up, as you'll see, and the latency gets longer and longer. And when the latency gets longer and longer, things start to break. Down here, this is where Jim started to notice because of his X Windows work. If you have a remote mouse, at 10 milliseconds, you start to lose the mouse. And over here, most VoIP applications start to go dead at 100 milliseconds. And around a little under a second, I don't know about you, but you're saying the internet's wrong. Why don't I refresh my browser? And you hit out here 8, 9, 10 seconds, you get things like networks start to collapse because of ARP. And the worst one I've ever heard was John Corbett was in a hotel and he was uploading his article, trying to upload his article to his website, and it wouldn't go through because there was enough delay in the network that whole article was getting buffered in the network. And then at the end, the SSH checksum would mismatch and it would say, hey. So, as the things go out logarithmic, things get worse and worse. Let me see next one. So the inventors of the internet sort of knew this. There was an early reference in one of the papers that said, congestion. This assumes the network doesn't have infinite queuing. Well, in today's world, we sort of have infinite queuing. We're no longer in the simple FTP universe. Google, for good reasons, increased the window size at the start of a connection to 10. We have nice, fast TCP algorithms, which I'll get to, that sort of make it worse. We have network offloading that makes So we have this whole set of things that has made what was a small problem back in 1985 to a really big problem in 2005. And what happens, go ahead, penguins, please. So what happens is what's called like head of line blocking. We have this one really slow guy who can't get through passport control, and all the penguins get stuck behind. That was me yesterday. And what happens also is, this is queuing theory basics. So basically, as every queue gets full, the delay goes to infinity. So if you have a really fast network, the blue one at the bottom, it looks really fast, really low latency, till all of a sudden you hit the wall and it goes off the end. If you have a really slow network, the green one gradually increases. So what does that mean? If you have really fast connections, you won't experience this until you finally hit the wall. If you have really slow connections, like you've got that 1 megabit DSL line that I'm ripping out of my house, it happens fairly fast. And one of the benchmark companies, Netalizer, did this. You can go run Netalizer on any connection. It will give you data about what your upstream and downstream bandwidth is and what your delay is. And what they did was they ran this and they put a dot in for every customer that ran the test. And what you see is, this is the buffer capacity. So basically how much buffering is in the network versus what their speeds are. So the people over here that have fairly high speeds have very big buffering. And these lines are what their buffer bloat is. So the yellow line is 1 second of buffer bloat, 2 seconds, 4 seconds. Well, you say, well, why is it white down here? Turned out that they threw those data points away. They didn't believe anybody could really have a network that was that bad. And the same thing is true the other direction. You have 1, 2 seconds, 4 seconds. A lot of people are stuck with huge amounts of buffer bloat. And when you have lots of buffer bloat, go to the next one after this. What happens is all your TCP algorithms start to fall off the cliff. All the TCP algorithms are designed to increase the TCP window, in other words, use more buffering until they reach the capacity. And when they hit the capacity, they try to stay in this region for maximum throughput. The trouble is when you have huge amounts of buffer, you get what's called a cliff effect. Basically, everything starts to go off the end and performance goes to zero. All the data is old, stale data. You're basically, it's like if you're filling your cupboard with stale cheese, it would just... And when this was first reported, everybody said, well, I don't see it in my system. It must be a Linux problem. Well, people have seen it. They just had started to work around it. The first one, in olden days in Windows XP, well, Windows XP only supported a TCP with maximum window size of 64K. So you couldn't really get enough data in the network to actually see it. Windows 7, what they did was they were observing this and they were noticing it as video and audio streams were getting chopped and delayed and weren't coming through. So they basically put a bandwidth limit in the consumer desktop of 80 megabits. Since most consumer networks were 100 megabits, they didn't see buffer bloat. And in Android, they saw the same thing. And what they did was they put a receive window limit in so that your Android phone won't get buffer bloat in the cell phone tower. And when Comcast saw this, they blamed the customer. What they said was, everybody's downloading too much stuff and it's slowing down our network. And so what do? Well, we'll block those people and we'll charge them more. It really wasn't the problem. And in fact, after the community got involved and we got the Comcast people involved, they changed their tune on this, and this is no longer what they're doing. So with that, I'm going to switch from the PowerPoint stuff to actually doing something way more interesting. And with that, first thing I do is I need a volunteer. Do I have a volunteer? Come on, send me, okay. So your job, the first demonstration here is here I have a network connection, and here we have a bunch of packets. Okay, well, I've seen, by the way, I've seen a much better demonstration of this, but I've never actually done it where everything was little beads or balls, but I think that would make made more of a mess. So the demonstration here is, I want you to pour these packets into the network. Come on.
Through this one?
Yes.
Okay, I'll try.
It's kind of slow, kind of hard. Okay, that's good. You can stop. So the first thing you do is, well, why not we use a tool? A tool is a queue. So you add a queue to the system, and now it's a whole lot easier, right? You can pour packets. That's good. You can pour packets into the network really fast. And what does this do? Well, this makes it so the buffering in this funnel adds up. It's very easy. You don't have to pour at the same size as this tube. You can pour faster and then stop. Well, if that's so good, why don't we use even a bigger buffer? The memory's cheap. Here, you can go ahead and pour that in. So you can pour you can pour it all in there. Come on. So you can pour it all in there. And you can take seconds worth of buffering. And so that works pretty well. Except then you decide that, okay, well, I really want to play something. Well, my packets aren't going through. What's happening? So with that, you really have a problem. So the first thing to realize is what's going on inside Linux. So what's going on inside Linux is we actually have what's called a priority FIFO. Now, the priority FIFO is kind of a super duper version of this bottle. I don't want to be spraying the floor because I kind of promised I wouldn't make a mess. All right. So what happens, thank you, with the priority FIFO, we have the normal data, and most stuff goes in the normal data. And then if you have something really important, it can go in the priority. Or if you're, you're deciding to download stuff, it can all go in the bulk. So what happens is there's basically 3 different queues, and they're prioritized. So this one gets first priority, this gets second, and this gets third. There's 2 fundamental problems with this thing. The first one is, who gets to decide which goes into which bucket? You may think it's simple. Well, there are some heuristics and marking that's in the system so that you can do that. The problem is pretty much everything always goes into normal. Nothing ever goes in the high or low priority. And then you say, well, if you're going to do that, why don't we be really smart and we'll do stuff? Well, if you start to get really smart, then people play games like, well, I'll always put my stuff in the high priority, or it'll be accelerator. The other thing is, when you get high priority traffic, it totally starves out everything else. There's no fairness. So there's no equality guarantees that everybody will get their fair share. So it's simple to implement. It's the default. But we know we can do better. So the next thing, you bring this up to the enterprise people, and they say, well, yeah, we have network guys. They're really smart, and they've taken Cisco classes, and they've tuned our network, and we have, which thing in Linux we call hierarchical token bucket, which basically means you have multiple different classes of traffic, and you can carefully adjust the valves. So each one gets their own set of bandwidth. So, the email system gets one set of bandwidth, and, our VoIP system gets another one of higher priority, but it doesn't starve everything. And, lastly, the guys who are using Dropbox or OneDrive, they get the bulk, and everything's fine. Well, you still have the same problem. You still have the problem of who gets to decide what traffic. And some traffic is just damn hard to classify. I mean, like the video you're watching in Facebook is buried inside the Facebook stream, and you kind of want that to have a different priority than the updates. And so pretty much everybody laughs, but in the internet today, all traffic's on port 80, and that just doesn't work very well for this model. The other thing, by the way, to mention is that every carrier strips off all the priority information when you leave your boundary. So as you leave your company, it's gone. It doesn't have any meaning on the backbone. So this is a good solution for enterprise if you have a well-controlled environment. And it pretty much also that's how Google at one was working internally. But as a good default solution, it didn't work out. So the researchers have an even better one, or they thought they had a better one. If you ask the IETF people, they say, well, we solved this back years ago. We have something called random exponential drop. And what random exponential drop is this one gets a bit messy. I think I need to pull out the tools here. I got it. So random exponential drop, also known as RED, is a queue where data builds up, but as the data builds up earlier, before you actually give up and start to drop things, you let some of it squirt out. So this one takes a little more than most. But if you can see it, there's holes. And as the data gets farther out, you let some of it squirt out. There's a whole bunch of them in this, and I guess it's not surviving. But this works pretty well, especially when you add in another thing, which is instead of just dropping the data, you go ahead and mark some of it. Sort of like book the hole back into here and mark it with a different color, which in the network is called the congestion notification bits. So you say, I let this through, but when I let it through, it was actually getting really pretty full. You should do something about it. So that's a good theory. There was two problems with this. One, the problem with this one is kind of like what I did was where to put the holes. How soon do you put the things? How soon do you start to drop things? How soon do you spray things out? The other problem with this one was it was really hard to set up. So almost nobody in the world, in the internet, ever ended up using this because it was just too hard to set up. And in fact, Van Jacobson, who invented it, wrote a second paper saying the problem with RED. He made one mistake, though, in the paper. He decided to use a plumbing analogy. He put a picture of a toilet in there. The editors of the paper said, that's not professional, and it never got published. You can get it, but it was never published. So, you want me to shift back? Okay. All right. The next one, which was the stock, one of the good stock solutions that existed before Linux started paying special attention to this, was stochastic fair queuing. And the idea behind that is instead of just having a few ones that are predetermined, we'll use hashing. So we take the water, we apply some hash to it, say this is green and it goes in this one. And we say, oh, well, this one has a different value. We'll put it over here in yellow. And so we have green and yellow, and each gets their fair share. And this works really well because we have like 256 bottles, which I just couldn't zip tie together. And we don't really have to have any special knowledge of the traffic. We just say each flow has a different hash value. It can go in a different bucket. And in fact, when you look at this, for well-behaved flows, this works as well as anything. And we didn't have to invent any new algorithm. But it doesn't work very well for single flows, and it doesn't really work any better than the original queue when things get really loaded. So as soon as the problem came up, Kathy Nichols and Van Jacobson and a bunch of other people developed something called control delay. And the way I like to explain control delay is here's a queue just like before, but when the data starts to build up, which is a little hard with these little bottles, what we do is instead of letting data fall off the top, we say data's been in this queue a really long time, and a long time is about 20 milliseconds. We say, well, why don't we just let some of the old data out before we get to the new data again. So the way that works is we mark each packet as it goes into the queue, and when we get down to the bottom, when we're taking these out, we say, how old is this? If it's old, start dumping till we get to the new stuff. And this behavior works really well, and it especially works well when combined with one of the other algorithms. So the favorite one for intermediate systems is called fqcodl, which is kind of like if you took each one of the queues in this and made it one of these, which once again would have been way too much work. So fqcodl pretty much solved the problem, and I'll go through some data in a second, for the general case of the internet. And one of the recommendations I made to people a few years ago, which seems much every distro has picked up, is make that the default queue discipline in Linux. So if you do that, pretty much all the problems go away in the worst case. But let's see. Here we go. So back. So the general problem is solved by fqcodl, and then the question is, can we solve the benchmarks as well? So the benchmarks were always measuring bytes a second, packets a second, and latency. What we really want to measure is throughput and latency, and we want to run multiple streams at once. So the first test that was done that way was called rule, which was a wrapper around netperf, which combined upstream, downstream, and doing ping tests at the same time. That is combined now into something called the Flexible Network Tester, Flint. And I recommend, if you're interested, it's really easy to run. And it gives you really nice, pretty graphs, which I'll show you some of them in a second, that show you what the real-time response under load is. The other two, which are more for desktop users, is ISC Netalyzer, which will report latency under load on a wide range of other stuff. And DSO Reports got involved with the Bufferbloat mailing list and made a cool test called speed test. And their speed test runs downloads, uploads, and measures your buffer bloat. This was run in a hotel. Hotel networks are kind of notorious for having huge amounts of buffer bloat. And this one had 5 seconds of buffer bloat. And that's caused by me running the test. In fact, the other one that's really bad is if you ever run this on airport plane Wi-Fi, and I recommend you don't, you will find 10, 15 seconds of delay, but you also run the risk of crashing the Wi-Fi's entertainment system. It's happened to people. And this is what the rule tests, the Flint tests, look like. There's a ping graph, which is the red one. There's upload, green, and download bandwidth. So you get a graph here over the life of the test. As in this case, you see with FIFO, we're up to 1 second of ping time, just induced from this other traffic. So the other traffic, the up and download, made the ping go even slower. This is the stochastic fair queue. So if you do the fair queuing, which is this one, your upload and download each hit different buckets, and the ping gets through with a nice constant. And go on to the next one. If you use controlled delay, you get a similar kind of behavior. Slightly longer ping times, but that's because that's where the controlled delay is starting to kick in. And if you run fqcodl, which combines the two, you get the best of both worlds. So going on to some of the recent changes. You know, are we there yet on solving buffer bloat? Once you look a little harder, buffer bloat, it shows up everywhere. The first people attacking it were Dave Tott and the Zero WRT project, which took up OpenWRT and added it to home routers. So you put FQCODL and a few other things into home routers, all of a sudden the buffer bloat goes way down and home networks behave better. The backbone providers and the network guys have gotten involved as well. It's a little longer lead time with the carriers, but they've started to realize the issue. And, you know, I don't know if you have it over here, but the US Comcast is advertising their Xfinity network of they can have 10 people using the network and there's no delay. Well, why? Because they learned from buffer bloat and they're doing things do better. But we still have things like legacy network accelerators, load balancers, other stuff that people have in their enterprises that really hasn't gotten the message. This is Dave Tott's list from his applying CODL to Wi-Fi talk, which shows you the whole long list of Linux versions. Pretty hard to read, but the first one that came in earlier before this was CODL, and then Google did something called byte queue limits, and byte queue limits was internally keeping the buffering down inside the Linux kernel. And there's pacing, a whole bunch of other things that are all related to how can we reduce the amount of data that's in flight in Linux before it hits the network. And the most recent one is TCP BBR, which I'll go to a little tomorrow. And on Wi-Fi, it just turns out that in Wi-Fi, everybody thought the problem was bad stations, too many people on the network. But a lot of the problems about Wi-Fi were buffer bloat. Basically, inside Wi-Fi, you have multiple layers of protocol stacks and multiple layers of hardware, and there was big buffers, really big buffers, trying to aggregate data. And you would get situations where the data aggregation would cause seconds of delay because it's trying to optimize something. So what Dave Tott did was took the Atheros driver, which because it's Linux open source software, he could put CODL into that queuing inside the driver and got much, much better performance. And this is the fairness graph. Well, so basically with Linux 4 stock, it was getting several seconds worth of, this is a second of latency. And then with his changes, he was going from a second to sub 4 milliseconds latency. So by just hitting one place in the stack made a huge difference to the perceived latency. So have we solved it? Yes, we've hit a whole lot of things. But a lot of that is technology done by developers, is a longer lead time to technology that shows up in consumer products. So it's going to be quite a while till all the stuff that's done shows up in the real outside world. And also one other plug, which is I don't have a good demo for it, is after CODL was done, Cisco developed something called Pi. And Pi is kind of like a same idea as CODL. It's used in home routers. It's used by DOCSIS 3.0 standard. And the reason that it's good is it gives you the same effect, but it was simpler to implement in hardware. So the real point of this is you could be over here, milliseconds of latency, but you're probably stuck over here on your network. And with that, I want to thank the volunteer by giving him the official lag kills. So thank you.
Thank you very much for this really nice presentation. And who has a question?
Yes.
Okay.
I could say loudly. So, you have presented really nice stuff. I probably will use it when I will renovate my pipes at home. Yeah, but my question is, what kind of scheme? Okay.
My question is, what kind of scheme could work best for low-speed networks? Because sometimes we have really starving for data, not overflow of data.
That goes to one of the fundamental things here, which I run into periodically with people, which is there's nothing you can do till you reach the bottleneck. So I can make this smarter if I have a lot of data at the front and only a little data at the bottom. If I have the other problem, there's not a lot I can do right here. Data's only coming in at a low rate. I can't do anything smarter if I have a bigger, faster network below it. I can only do something smarter where the transition between fast and slow is, where I get some data accumulated. I can either be smarter about how I do it, or I can pour at a different rate so that I don't overload it.
Okay, the next question. I think that while everyone is thinking about the questions, probably you can tell us a couple of words about what you will be present tomorrow, because it's also interesting.
Yeah, tomorrow I'm going to go over recent advances in the Linux networking community, and I'm going to go a little bit about TCP, PBR, other projects that are related to networking performance, kind of a survey similar to, I don't know if you've seen the kernel reports that Jonathan Corbett does for the whole Linux kernel.
Thank you. Questions? Okay.
Yeah, you mentioned that we basically didn't solve the problem for end users yet, for a bunch of problems, because we have a lot of infrastructure between endpoints. When do you expect this problem to be universally solved? Will it take 5 years, 10 years? Is there a consensus between vendors like Cisco, Juniper, whatever vendors of networking equipment that this is important, that needs to be solved, just end to end?
It is solved. Okay, there's two questions going on there. One is, when will it show up, and are the vendors are aware of it, and they've definitely, everything in all their products, proprietary or open, has that as an important element. As far as solved, we may get it solved by a really odd effect, which is, I don't know if you guys seen all the DDoS attacks lately, and home routers are being used to do that. So I suspect that those are going to get accelerated replacement. So 3 years. And a lot of the other thing is, I don't know about over here, but in the US, the providers like to do a thing where they lease you the gear. So the home router you don't actually own, you're paying $10 a month for that router. And if you're paying $10 a month, all of a sudden the responsibility goes back to them to replace it, and they're more likely to replace it faster. So there's some business background things that may cause it to happen faster than I used to think.
Thank you.
Next question.
To fight the Bufferbloat problem, basically you throw packets away instead of queuing them. So,
well, no, there's two things. One, you throw some packets away instead of queuing them. You also divide and conquer. So if you divide things up, it's, in this case, it's not so much that I'm throwing them away. It's that I've divided up the flows into different buckets. Because I've divided them, even though each one of these things might be really big, yes, the overall fairness is still in place, and so like my ping time doesn't get too bad. Yeah. You still can't make the streams behave any better. Yeah. You just made the overall.
Yeah. But the dividing is not enough. So for the throwing away part, yeah, isn't there ever some loss of throughput because you're throwing something away?
Well, with TCP has some interesting dynamics here. One of which is if you throw packets away sooner, but not as many, then it adjusts to the effective bandwidth better. You know, remember that curve? If you start to throw away sooner before you build up seconds of latency, this whole overall system behaves better. If you wait until you have seconds of latency, by the time you get to throwing things away, you're throwing seconds of data away. In other words, by the time the next burst comes, all of a sudden it's a huge amount of data, and it doesn't matter how big your queue is. If you're still getting, a meg of data, if you're still getting more and more data, you're still throwing that away. So its recovery, it ends up crashing back. It crashes its whole throughput back to a very low rate. Whereas if you can lose just little bits of data, it can adjust itself and achieve steady state. Yes.
Okay, please wait for my microphone.
If you shake your bottle, would be more fair?
If I what?
Shake. Just pick up random data from the bottle.
If I threw stuff away at random, that's what red does, and it does.
If we use pseudo random algorithm for taking data from.
Oh well, they do. That's kind of what red does, and also a bunch of other ones do. The problem is, how do you determine the percentages of the random? So you end up having to adjust. You have a lot of parameters to that algorithm, and those parameters are hard to set without knowledge of data capacities and throughput rates. You basically end up having to have a mathematical model of the system to determine those parameters to create the random algorithm.
Thank you. The next question. Okay, you'll be the first.
Sorry. Hello. But have you said that there was were lots of difficulties with this configuration of this smart bucket? But have you ever thought about that as an optimization task? There is a class of optimization algorithms which show very good results with data which we are not very lot about. So we don't know how we want to configure this amount of buffer and the amount of data packets which we want to drop. But if look at it as an optimization, from the optimization point of view, we want to maximize buffer and minimize latency. And we could find some solution like gradient stochastic or something like that.
Yes. Okay, your question is, have people done these models to do smart optimizations? And the answer is yes, but there's really there's kind of like two ways to attack this problem, and I kind of wanted to do a demo and didn't really have a good way of doing it. If you go back to the simple case, there's two ways to make this smarter. Yeah. The one way is I can make the bottle smarter. The other one is make the human smarter. And a lot of work has gone in recently, and I'll talk a little bit about TCP BBR tomorrow, but basically make the human smarter so the human pours at a smarter rate. So if you do that, you basically control the input rate to the system with smart algorithms. Then you don't have to make the part that's hard. You don't have to make the queuing algorithm smarter. You make the admittance algorithm smarter. I haven't known anybody who's done a lot of work on really super smart queuing. They've done work on smarter TCPs.
Thank you.
Okay, the next question.
You're talking about Linux, and is the BSD approach different?
Yes and no. BSD has a lot less infrastructure in place to deal with this, but there has been some work in taking parts of this, like the FQCODL stuff is BSD licensed, and some of that is made into BSD, but a lot of it is not on by default, and it doesn't seem to be as much of a focus of that community. It's there, it's just not turned on as much.
Okay, next question. And by the way, вы можете спросить по-русски, я попробую перевести.
Okay, thank you. In your slides, I've seen that TSO can increase latency. So question is it good technology, TSO, or we need to switch it off when we use on desktops?
That's actually a really good question. You asked about TSO, which is TCP segment offloading. And what that does is, maybe to use my last bottle. If you have a really big, if the application is sending a big amount of data, it can be preserved all the way through the TCP stack and then broken up at the hardware at the last little bit. And the hardware basically breaks it into one big packet. And the problem with that is all of a sudden that one very big packet maintains itself all the way through the network. And when it finds a choke point, causes a big amount of buffer bloat. So what Linux has done to address that is it right now, at least internally with the TCP small queues and other things, it adjusts the amount of the size of that TSO frame to be what it perceives as not going to cause buffer bloat. So if there's other things going on, it will keep it smaller. If it doesn't think that it's actually going to need to send that much data at once, it won't send that much. So there's a heuristic that adjusts that. I don't know if I was doing, a VoIP server or something where I knew that I didn't want my traffic to I wanted better spreading of data, I would turn it off, and I wouldn't be surprised if some of the big cloud providers turn it off. But in general, it's not that much of a problem. All the benchmarks here and everything are run with it turned on.
Okay, I have a simple question. You point us what was done, but what will be done next after this in the kernel?
That's always hard to answer.
Yeah.
I think that the two people that are driving this are the cloud providers and the end equipment stuff. And I think the end equipment stuff, the answer there is the Wi-Fi work will be applied to other technologies and wouldn't be, because a lot of the Wi-Fi chips do this in hardware, so the hardware could be smarter. So on the consumer side, we can have smarter edge routers, and on the cloud providers, they're all trying to give you your Facebooks, your Twitter, whatever thing, LinkedIn at scale. And so they're always optimizing the algorithms, refining them.
I see. And what will be the difference with 100 gigabit Ethernet, for example?
100 gigabit, the problem is the buffers you get the inverse on a lot of the equipment. At 100 gigabit, the buffer is very small in terms of time. So it becomes even more important to not send huge amounts of data, because once you get to that transition between the 100 gigabit and the 90 gigabit or Sonnet or something else, the fact that the buffer is so small means if you slam it with too much data at once, it will fall over right away and get data loss. So I think at 100 gigabit, the problem becomes not too much buffer, because you have to optimize for small buffers as well.
And what is there any difference between standard Ethernet frames and jumbo frames?
Jumbo frames, the latency can be long. They're kind of like TSO. The latency can be longer, but unless you get into the really super duper jumbo frames, it's not a big problem. I don't think that we're really talking about the, stacks of megabytes of data, and and the 64-byte frame can't get through.
Okay, thank you. Another questions. Okay.
Hello, not sure if you know that, but what about our enemies, like Windows and Mac OS? So what do they do with that problem?
Well, I've met the Windows team. The Windows team has a bunch of things they do internally down at the QDIS layer that are similar but different. I mean, different technologies but similar ideas. And also, the Windows current versions of Windows use compound TCP, which behaves similar to Cubic but isn't as aggressive, so it's a little bit better. Mac OS is on a totally different planet, and it has kind of weird behaviors, especially on its ACK behavior. I've seen bugs, but I'm not sure exactly what they're doing internally to address the issue.
That basically means if we are talking about wireless network and we have a lot of Mac OS or iOS clients, they may produce a lot of problems with Bufferbloat because they will do something we don't expect.
Right. Well, it's in the Wi-Fi case, it's more the access point that has the problem. Because once again, where buffering is the problem is where you get lots of fast things coming into a slow thing. So with the access point, you get the situation of data coming in from multiple clients, and then you have one pipe, and likewise coming back. So that's where the worst problem is. As far as the Wi-Fi on the client side, it's less of an issue unless you're playing a YouTube and a game or something at the same time.
Thank you.
Well, next question. Вопросы? Okay, another one from me. Could you tell us a story how you work in Microsoft now?
Oh, well, that's actually the short story is I was working at Brocade and doing their vRouter, and it was pretty much a solved problem. The team was working really well, and Microsoft is now growing Linux in Azure as it's faster growing than Windows in Azure. So we have 30% of the clients in Azure are Linux, and it's going to be 33, 50% pretty soon. And so they said, can you come help us optimize that, make it smarter, make networking better? And so you'll see lots of upstream stuff. Yep. And it also goes the other way too. It's like internally I'm working with other teams at Microsoft to say, okay, we can make Azure and Hyper-V run Linux better. What can we do to make the protocols work better between the two?
Thank you. Another questions, guys? Okay, looks that we covered pretty everything. Thank you very much for your brilliant presentation. And we'll see you tomorrow.
Okay.
So, thank you.